Hello friends, welcome to engineering tutorial. So today we are going to resume our discussion on another important subject. So waves and oscillations. Will take our discussion forward from where we left it. So we are discussing about simple harmonic motion. So I would request you to please watch the previous videos in the waves and oscillations playlist. So I think 6 or 7 videos are there where I've discussed the basic things related to waves and oscillations, and we just touched the concept of simple harmonic motion. Sorry. So we just discussed about simple harmonic motion, and in this video we are going to discuss about the general displacement equation of SHM or simple harmonic motion. So just to quickly recollect all the basic things, simple harmonic motion is an important type of oscillatory motion in which there is a to and fro movement of a particle or a body about an equilibrium position, center position or mean position, whatever you want to call it. So there is a kind of to and fro movement. For example, here the particle which is originally at the mean position or the equilibrium position or the center position O, it undergoes to and fro movement between the two extreme points P and Q, which are equidistant from this mean position O. So this is a basic example of simple harmonic motion, and the variation of the displacement, the instantaneous displacement with respect to time, it follows a sine or cosine waveform. Okay, and we also discussed the correlation between uniform circular motion, that is movement of a particle along a circular path along the circumference with a certain angular velocity, with simple harmonic motion, where the movement or the position of the particle on the circumference and that measured from the center, when we draw a perpendicular from that point to the diameter of the circle, we compared that movement with the simple harmonic motion, that is the movement of this particle, the diameter, the perpendicular which we draw from that position, instantaneous position of the particle from the circumference to the diameter, that position along the diameter is an example of simple harmonic motion. And we also determined the displacement equation, which we got as y is equal to a sine omega t. Okay, so here a is the radius of the circle, omega is the angular velocity, and t is time. Now this is the simple representation of simple harmonic motion, but here we assumed that the position, the initial position of the particle is from B. Okay, so that's why we got this equation. But most of the time what happens is that the initial position of the particle along this reference circle, it is not from the origin position, or the reference position is not B. It can be anywhere along this circumference. So for that case, let us say we have taken another circle, and let us assume that the initial position of the particle is P0. Okay, it starts from P0. So the angle of this point, it is given as phi in anti-clockwise direction or counterclockwise direction. So in that case, this angle POB, okay, this angle B, that is phi, becomes an important part for the mathematical analysis of simple harmonic motion. So in the upcoming videos we'll discuss about the characteristics of simple harmonic motion, where the concept of phase angle will come into play. So this is the phase angle, okay. So basically it is the position of the particle or the object at t equals to 0. So this equation a sin omega t, which is a simple representation, mathematical representation of SHM, gets modified to this: a sin omega t plus phi. Okay, this phase angle, it gets added to it, and this is related to the initial position. Okay, this omega t plus phi, this thing. So when t is equal to 0, then this whole thing, omega t, it becomes 0 and only phi is there. So that gives us information about the initial position, because we know that this OM by OP here, OM by OP, this OM gives the position of the particle along the diameter. So from the initial angle, this phi, okay, this phi, we can get information about y, the instantaneous position of the particle. Okay, so that's why this is the general displacement equation of SHM, taking into account the full description about the initial position. Okay, so this whole concept of phase angle comes into play. So similarly, let us say here where the position is P0, the phi, it is somewhere in between 0 and 90 degree or pi by 2 radians. Suppose the position is here, somewhere here, then it will be greater than 90 degree, lesser than 180 degree, or greater than pi by 2, lesser than pi. Similarly, if it is B dash, let's say it is starting exactly at B dash, then it will be 180 degree or pi radians. Similarly, if let's say it is somewhere here, then it will be greater than 180 degree, lesser than 270 degree, or greater than pi, lesser than 3 pi by 2 radians. Let us say it is starting at A dash, so we can call it minus 90 degree or plus 270 degree. So likewise, depending on the position of the particle on this reference circle, the value of phi, that will change, and that is very important when we consider the simple harmonic motion equation, because the whole position, the position of the particle or the instantaneous displacement of the particle depends on that parameter. This omega t plus phi, it is very important when it comes to determining the position or the instantaneous displacement of the particle undergoing simple harmonic motion. Okay, so this is just an important thing related to the general equation about the instantaneous displacement in simple harmonic motion. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.